Anyway, welcome to FS2 Talk by Fabio Labella. I am Yurios and I'm team lead for Ironbank. These days we're called direct debit networks and we are in the core banking domain. The team has been doing Scala for quite a while. Actually, those who first introduced Scala to the team are in this room today. Very recently, we started a more functional approach, and we've been using a set of very core libraries to achieve that. And one of these libraries is FS2. Fabio is here to talk about FS2. He is one of the core contributors for this library and advocate for the pure functional paradigm in Scala and in other languages. So with this, I will hand over to Fabio. We'll run this, and then we'll have the usual drill, some time for questions in the end for Q&A. Enjoy.
Cool. Thank you very much for having me. I've been working with Ironbank the past couple of days. It's been great. So I hope you can like the talk. And if you don't, you still have food, I guess. So it's great. So I aim the talk at a sort of general audience because I imagine varied backgrounds, but just to get an idea. So how many of you have some familiarity with some functional-ish static programming like Haskell, Scala, or Camel? Whoa, a lot more than I was told. And how many of you have familiarity with stuff like Clojure or Ruby, kind of modern, dynamically typed stuff? Yes. And what about Java? Nice, cool. So this talk is a talk about FS2. And FS2 is a purely functional Scala streaming I/O library. But what this talk is really about, beyond this detail, is a talk about declarative program flow. So it goes beyond just using this library. It's just the idea of having this way of having this program flow written declaratively in a very expressive and composable manner. So who am I? My name is Fabio. I am a senior software engineer in the financial industry. I'm based in Edinburgh, in the UK. And I am also a pretty active open source author, mostly in Scala, functional programming subset. So if you are familiar with the ecosystem, I am one of the co-contributors and maintainers of FS2. I help maintain CAS-Effect and HTTP4S, and I contribute to CAS, Shapeless, and all those. If you're not familiar with the ecosystem, I write a bunch of purely functional code that helps other people write their bunch of purely functional code, and it's great fun. Yes, so I'm in like slide 3. I've already said purely functional programming 4 times, so I guess it's a good time to kind of explain what it is. And the reason I want to do this is because it's often explained really, really wrong. And so it's like, okay, purely functional programming is programming without side effects. And that's true. Okay, what are side effects? And you go, well, writing to disk or mutating state are side effects. So purely functional programming doesn't do I/O, write to disk? So how do we get anything done? And then they go, well, because it's not really pure. You know, you have a pure subset, and then you do side effects. But then why purely? It's just all wrong. And the catch is the definition of side effect. That's you know, people get this bit wrong, and then they get everything else wrong. So purely functional programming is about purity. But purity is not a moral quality. It's just a very precise property, which is better known as referential transparency, which is you can always replace an expression by its bound value without changing the result. And even though you might or might not have come across the term, it's actually a very simple term because everyone who's done some middle school math is used to this. So if I tell you x plus 1 times x plus 2, and I tell you that x equals 1, what do? Or x equals 3 or whatever. You put 3 everywhere you see x, and then you reduce the expression. So purely functional programming just means we want to be able to do the exact same thing with our code. And hopefully I'll show you how and why you want to do this. So let's see if we can do this or cannot. So we have this string, hello, and we call reverse on it, and then we concatenate it with itself in the value below. And the result is hole hole. And then we want to apply this principle, so we will replace x with hello reverse everywhere we see x, just you would do with 3 if it was a math expression, right? And we get hello.reverse plus plus hello.reverse. And the result is the same, hole hole. And this is pure. Yeah, great. So let's try another bit of code instead. So we have an int that is read from the standard input, and then we add it to itself. So what's going to happen is going to read one thing from the standard input, say 2, and then 2 plus 2 equals 4. So again, let's do this very simple thing of replacing things and see what happens. So you get readInt plus readInt. But now what's going to happen is that we're going to read twice and then add both. So this thing is not pure. And the reason it's not pure is because we've broken that property. That's the only reason why it's not pure, by definition of what pure means. So let's do it again with future. So for those of you who are not familiar with future, it's like this asynchronous abstraction in sort of mainstream Scala, similar to completable future in Java. So we do the same. We say, well, I want to read it asynchronously from the standard input. And then this mapn thing is just like combining 2 futures so that you get another future that waits for both and sums the results. So you get another future back. And it's the same thing. You're going to read once because you read the first time and you get the result. And when you read the second time, you get the result that's already there. So 2 and then 4. And then you apply the stupid substitution, future readInt mapn plus, and now things have changed again because they both going to evaluate separately, and you get 2 queries from the standard input. So this is also not pure. And now people assume that reading from the standard input is not pure. But that is not the case. This is not why. The reason why this is not pure is because of the property. And in fact, we have in the FP ecosystem, I've created a thing called I/O, which looks like future, but with a crucial difference. So I create I/O readInt, and the difference is that I/O will not actually read from the standard input. It will just say, well, I know that you will want to read at some point. So when you do read and read, you're saying, I know that you want to read twice. And so actually, when you execute this, you do 2, 3, twice. Just because that thing is not executing anything. It's just literally the definition of what you want to do. And I say why you run it because since I/O doesn't do anything, it doesn't run by default. What you do, you compose these I/Os together in big, massive I/O. And at the end of your program, all of your program is one I/O. And then you say, OK, now I want to run it. But at that point, you cannot observe the fact that it's running anymore because it's the last thing ever in your code chain. And so when you do the replacement, you get the same result, 2, 3, 5. And so, woo, pure. We have done purely functional I/O, the very thing that seems impossible when people tell you that it's a thing. So what is pure FP then? Pure FP says that side effects are things that break referential transparency. It's not about reading from the input. It's how do you read it? Do you read it in a way that respects this property? Or do you read it in a way that does not respect this property? So I/O, state, and so on are traditionally side effectful. In Java, they're side effectful. In mainstream Scala, they're side effectful. But they don't have to be. We can build abstractions that respect that property. So now that you all know what purely functional programming means and why it's not an oxymoron, why is this seemingly small property important? Why should you care? And the reason behind this is that referential transparency implies local reasoning. So the fact that you can always replace an expression means that all that expression needs is its input, and all that expression does is its output. There's no context. And so to understand something, you just do this replacement, and you can understand it in isolation, and then put it back together. Just like you can understand any sub-expression in x plus 1, by replacing the thing, and then you do it on the other side of the equation, and then they put back together. And local reasoning is why FP is nice. Because what we want to do when we understand code, we want to understand bits, the bits of code separately, and then put them back together in a way such that the behavior of the whole is the sum of the behavior of the parts. And conversely, when we build code, we want to build it by building little pieces, and then composing these little pieces together to create complicated stuff, such that the behavior of the complicated stuff is the sum of the behavior of the small parts. So that feeling that I think everyone has experienced of having too many things in one's head, you know, it's like, oh my God, I'm about to lose it, and now someone is going to interrupt me with an email, and I'm done, and I have to start again. This doesn't happen, because you don't have to all things in your head at the same time. And that's global reasoning. Where you have a side effect, so if I say read on a future, you don't know whether it's going to execute or not, because it depends on whether something else in your program has executed first. So you now have to have the context of this part of the code and this part of the code. You cannot just replace the definition in each side, because the behavior is going to change. And again, this point is like the simplest point in pure FP, and also the hardest point. Like your pure FP journey starts with understanding this property, and then it kind of ends when you fully understand it. And you only truly do, in my opinion, when you write purely functional concurrent code and see how it differs from non-purely functional concurrent code. So just have to take my word for it, unfortunately. So this is pure FP. And now what we're going to do is, since now you all know pure FP, we're just going to jump straight into how to write code with FS2 in pure FP and see how that flies. So FS2 is a library whose main abstraction is a thing called stream. And a stream is something with two type parameters. So before we go into what this is, I just want to give you an intuition for what it wants to express. So stream is something that can emit 0, 1, 2, n values, where n can be infinite. And an infinite stream is a perfectly fine thing to have. It's not like a problematic or pathological case. We can deal with infinite streams all the time. During emission, it will request effect in F. So when I say effect, it doesn't mean side effects. It just means doing something, and it's not a side effect because it does not break referential transparency. And what is this F there? What does it stand for? Normally, it's just I/O. So when I say a stream I/O of int is a thing that will emit 0 or 1 or 4 or infinite ints. And to do that, it will request effects in I/O. For example, read these ints from the standard line, or do all sorts of things in there. And in this talk, I'm going to specialize F to I/O all the time. So sometimes you're going to see signatures with I/O. They are actually not specialized to I/O. They are polymorphic in the F, just to keep things a bit simpler. So examples of what you can do with a stream. So the first one is just a non-effectful stream. It's just emitting 1, 2, 3. So it's the equivalent of a lazy list. It will emit 1, and then emit 2, and then emit 3. The second one has this eval thing that takes a single action in I/O, for example, print line, and then creates a stream that will evaluate the action and emit the result of the action. And notice we have these two layers. We have print line, and then we have I/O, and then we have stream. So print line is like our impure Scala. And then with I/O, you say, OK, now this is pure. We are in the realm of functional programming because of that, not executing things. And then we say, OK, I want a stream that evaluates one I/O. And then I've got just a random combinator taken from the library, repeat eval, which will basically repeatedly evaluate this action. So what you get with this is a stream that will print hello all the time.
So the first example, what would the type
Great, great. So that's one of the things I wanted to end with. So it would be stream pure A. We say we have a concept of an identity effect. And then we can say every time you have a non-effectual one, you can lift it into an effectual one because it's a subset of the other. Whereas this other one is stream I/O unit, and the one is also stream I/O unit. But you can convert non-effectual ones to effectual ones, but obviously you cannot go the other direction because it will mean side effects. So this one is an infinite one, and we'll see why you want to have an infinite stream and what you can do with it. And then how do you actually do stuff with streams? So you compose all these streams together. You compose your programs of streams. Then at some point, you want to say, well, I want to compile this stream DAO to a single I/O. And this single I/O describes the action of running the stream and doing stuff with it. And we're still pure at this point, because the return type is still I/O. There's no side effects anywhere. And so you can either say this is the final one, or you can compose it with other I/Os that aren't coming from FS2. And then at the very, very end of your program, as the last instruction in main, the very, very end, you say, well, run the I/O. And if you do this not at the very end, then you've broken pure FP Scala. Scala is not a purely functional language, so it requires discipline from you. So don't do this, and it's called unsafe. And people don't understand why it's called unsafe. I don't know what else we could have called it to make sure that you never call it. So it's not unsafe as in it will crash your memory or anything. It's not unsafe as in Java unsafe, MISC. It's unsafe as in you leave the nice world of pure FP and you go into the hard world of normal programming, I should say. So yes, so this is what like a stream is in a nutshell. So what I want to do now is give you some intuitions on how you operate on these things. How do you combine them together? What do you use them for? And okay, first of all, let's say we want to do some normal pure I/O. And by normal, I mean non-streaming, which hopefully will become clear in a second. So we have this function from list to list. So a simple function. And we filter on this list of strings by taking the strings that are non-empty and the strings that don't start with a comment. And then we map on each string by putting it to uppercase. And then we take the first 100 strings from there. So the reason we like this is because it's composable and because it's declarative. When you compare with you can do this with a while loop, but then the logic of filtering and the logic of mapping are normally intertwined. You say while, and then you say if, and then you say to uppercase. It's non-compositional. Compositional means that every part makes sense on its own. If you just see a filter, if you just see line 2, that it's a thing that makes sense on its own. If you just see map to uppercase, that's a thing that makes sense on its own. And we compose things by aggregating and manipulating things that make sense on its own. And the nice thing is that the thing we have created also makes sense on its own. And so that's how you deal with complexity. You build these things and they are independent. Doesn't matter if it's a very small map to uppercase or it's a big system that does I/O and all sorts of things. If you do it purely functionally, it will be a self-contained unit that you can keep composing. And this scales, because if you do it the other way, like where you keep everything in your head, no matter how good you are, at some point, you'll reach a stage where it cannot fit in your head. And you cannot split it down. Whereas with this, you do this, and now I can ignore this filtering, mapping, and taking. I can say, convert non-empty to uppercase, and that's a single thing. And then I can keep doing this and build complex things compositionally. And there's a million talks about this concept, so check Runer talk about composing programs for more on this concept. Now, if I want to do this with effects with a file, I have an I/O of list string, and just say, well, wrap, read this from file. I'm assuming this is a Scala or Java side effective one in I/O. Now it's pure. And then map on the I/O will basically let us access this inner list here. And we do process. So what's happening, we read the list with I/O and then do that processing. And again, I'm going to say we read the list. I/O doesn't actually read the list until you say run the final thing. But I don't want to repeat this point on each slide. So this is all cool. The problem with this is that it requires your list to fit into memory. You need to read the whole list because process wants the whole list. So what if your list does not fit into memory? What do you do then? Then you have to resort to kind of imperative looking code where your I/O will read a chunk of the file and then you will do a recursive function on the next chunk and manipulate each chunk. And that's still pure because it's in I/O, but we lost a nice declarative way of doing it with map and filter. So can we have both? Can we have effects in I/O and keep the nice compositionality and and expressiveness of combinators. So the first use case for FS2 is what's called streaming I/O. So we have this example, and there's no need to understand the mechanics of it. Hopefully, it's kind of clear what it does. So read all from that file, and then decode so that the bytes are interpreted as UTF-8. Split by line, that's what text lines does. Filtered lines, there are non-empty and non-comments. Do that Fahrenheit to Celsius conversion above. Put a new line after each number, and then encode through UTF-8 again, and then write it into another file. Now, if you look at this code, it looks like, when I say read all, it reads the whole file into memory, and does all this transformation, and then writes it all into a file. But this is not what it does. What it's doing under the hood is actually read all returns a stream of byte. And so if you remember the concept of emitting things, it's actually emitting a chunk on each thing, and actually doing streaming. So it will emit the first chunk, encode the first chunk, split the first chunk, and then keep going that way. So you don't have to fit the whole file into memory, you just fit a chunk at a time. And this is called streaming I/O. This is what streaming I/O is. And in this case, the chunk, you can decide it here. So like, how many bytes of the file do I want to read at once? But the important thing is the concept. So this is the first thing that FS2 is good at, and this was the original motivation for FS2 way back. And most people only come to FS2 when they need this sort of thing, when they have some data that does not fit into memory. And conversely, if they do not have data that doesn't fit into memory, if all their data is small, they don't think of FS2 as something that they might benefit from. But the point of this talk is show you how stream is actually a lot more useful and a lot more powerful than just this original use case of streaming I/O. And actually, the vast majority of my FS2 usage, my data is small and it does fit into memory. So why do I still use this, even if I don't have that requirement? And it's for control flow. So I want to step away from the streaming aspect of it, even though you still get that benefit on top of it. And I want to focus more on how we do use stream for control flow. And the reason is you might not have data that is too big every day, depending on what you do, but you definitely do have control flow every day if you write code. So it's more applicable, I think, to your experience as engineers. So to understand how FS2 works, the initial intuition, you can imagine a sort of list on steroids. And by saying list on steroids, I mean two things. First of all, a list cannot do effects. Obviously, you can call into side effects for Scala in a list, and so you will have side effects. But then you've broken the previous thing of compositionality. But if you start wanting to do purely functional effects with lists, list doesn't really do that. And also, a stream is lazy, can be infinite, so it's kind of like a more powerful list. And the first way of seeing this is by talking about one of the primitive operators on stream, which is ++, which means concatenation. So if we have a normal list, we say list range 1 to 100. It creates a list of 100 elements. Take 3, it will take the first 3 elements, and then add it to a list of 21 and 22. And the result is list 1, 2, 3, 21, 22. Similarly, we can say this. So I've created a little function here, put, that takes a string and returns an I/O of unit. And it needs to return an I/O because it needs to be pure. And then I'm going to say, just look at this bit from there to your left. Stream repeat eval, put hello. So that's an infinite stream that will evaluate that action all the time. But since stream is lazy, it's not actually starting to do it. It's just like I'm describing the fact that I want an infinite stream that always prints this hello. And then when I say take 3, in a list, you just take the first 3 elements. So in a stream, you just evaluate it the first 3 times. And then just as ++ means do this first list and then append the other, In a stream, it means emits all these elements, and once this is finished, then you're going to emit the other. So what happens here is that I print hello 3 times, and then I print world. And if you look just at repeat eval, that's an infinite stream that you might think, oh, it doesn't make sense to have an infinite stream. But obviously it does, because you then are going to manipulate it in a way that will make sense. And yes, so the first thing is that ++ kind of means after this stream, do this other stream. So do this and then do that on a kind of timeline. Similarly, you have flat map on a list. So I have a list 1, 2, 3. Flat map for a list literally means map on each element with another list, and then flatten them all into one. So what I'm saying, for each element in the list, I duplicate it in a list of 2 elements, and then I concatenate them all together. And so what I get is 1, 1, 2, 2, 3, 3. And on a stream, I can do the same. I have the same, purely functional print line there. And I say, well, create a stream 1, 2, 3. And then for each element, same thing, repeat eval, put, but take 2. So I'm creating, on each element, I'm creating another stream that prints it twice. And when you do the flattening bit, we are using that concatenation operator that we just seen on the slide before. So this is sequential. It's going to emit the first one, create the stream, finish with the first stream, then start the second one. So take the 2, create the second stream, do the second stream, and then the 3, take the 3, create the third stream, and then do the third stream. And so you get 1, 1, 2, 2, 3, 3. It's a very simple list on steroid, thing. Now, a small interlude is that even within FS2 itself, we do believe in compositionality. So we don't want to have 45,000 primitives that are used for creating streams. And actually, we only have around sort of 6 or 7, depending on how you want to count them, like less than 10 anyway. So eval is a primitive, so how to embed an IO into a stream, and ++ is another, like you get 2 streams, and you create another stream. That means do this and then do that. And this is why I mentioned the thing about IO. They're actually not specialized to IO. It's just for simplicity in the slide. And then when you want to build other stuff, you can say, well, I want to create a repeat thing that takes a stream and creates an infinite stream that just repeats itself. So this is in the stream class. That's why you see this there. And what does it mean to repeat a stream? It means, well, myself, this, and then I'm going to concatenate to myself, repeat, which in turn means myself, and then I'm going to concatenate to myself and myself, repeat, and then so on and so forth. So you've got this infinite stream that just means do me, and then I'm going to do myself after me, and then I'm going to do myself after me, and so on forever. And repeat eval, you just do, well, eval, and then repeat. So even within the code base, most operations are exactly what you would expect them to be if you were to write them on your own. And if you compare, for example, with Akka streams, for those of you who know it, which has got like 25 different concepts that you need to, I think this is nicer to learn and to use. So we have not very many primitives and lots and lots and lots of combinators. And then a third operation I want to mention is zip. So you have a list 1, 2, 3 and another list ABC. And when you zip, you just do pairwise aggregation. So you get 1A, 2B, 3C. So what does it mean for a stream to be zipped with another stream? So again, I got this purely functional print line. And I have a stream range that will create 10 elements. And eval map just means do the IO on each element. So it's going to say, it's basically going to print each element on their range. So it's going to print 1, 2, 3, 4, 5 as fast as possible. And then I have another stream, awake every. And what this stream does is going to emit something on every second, just like I said. So imagine you've got this fast stream that prints 10 numbers, and you've got this going on each second. And so just as zipping on a list means putting the elements together, zipping on a stream means emitting at the same time. So what I'm doing, I'm forcing the fast stream to go at the same pace of the slow stream. It will wait for one element on each side and be emitted. So the result of this is that you're going to print 1, 2, 3, but once every second. So 1, 2, 3, 4, 5, and so on. And again, compositionality. This makes sense on its own, the print fast. This makes sense on its own, the tick, and we put them back together with a combinator to achieve the behavior that we want. Yes, so obviously there's more. There's a lot more operators. And I cannot cover them, not even a subset of them. But I guess what I wanted to give is this intuition of a stream like a more powerful list that can embed effects. And hopefully you can kind of start to reason about the FS2 code, which we are going to see with this intuition. And yeah, come and ask questions later if it's not super clear. So, example. So this example, I think, is pretty cool. First, it's used in almost every FS2 talk. I have written it in my code. And then as it turns out, working with Iron Bank, we had to implement the same thing. They were actually implementing it not with FS2. Well, not quite the same, but pretty much the same. So we have an health check. So imagine there's an API, and it's a flaky system. So we have to call this API to make sure that it's up. So imagine this I/O response, that response being an HTTP response, and that I/O is a single action that does one REST call. So what we want to do, we want to do this health check every 5 or 6 minutes, right? But for each call, if the call fails, we don't want to give up. We want to do some retries, and we want to do these retries sort of with a linear backoff. So on each call, if it succeeds, fine. If it fails, I'm going to retry until it succeeds. And this thing, I want to do it every 5 or 6 minutes, which is something that happens quite a lot in server-side code. And just if you imagine how to do it imperatively, you have this first while loop, then you do a try-catch on the thing, and then if you have a try-catch, then you have an inner while loop that does the retry, doing try-catch again. And then outside you do a thread sleep, to wait, and yeah, it's a bit crazy. So how do we do it here? So let's look at one line at a time. And the reason we can look one line at a time is because of compositionality. If this thing wasn't compositional, we couldn't look one line at a time and then understand what everything means. So the workhorse for this is this stream.retry, which takes an action. It takes the initial interval, and it takes a function to increase the interval on each failed retry. So I'm saying on each retry, increase by 1 second, so linear backoff. And then I'm also saying I want to try maximum 5 times. If it fails for 5 times in a row, then enough, error out. And I guess it's a good time to mention errors. We don't throw exceptions ever. A stream has a concept of being in a failed state, and we have combinators to handle this failed state so that everything is nice and it doesn't blow in your face. And I'm saying, so retry is going to do, if it succeeds, it's just going to emit the success. If not, it's not going to emit anything. It's going to keep retrying. And if it cannot do it, like by any means within 5 times, then it's going to error out. And the line just below says, well, on error, just return error response, which I'm assuming is something I already have to describe this response. And this makes sense on its own. This is a stream that does retry and makes sense on its own. You don't need to know about the rest of the code to understand what it does. And then I have another stream that makes sense on its own, which is okay, do this action, and then sleep for an hour, and then repeat myself. So it's going to do the action, wait, and then repeat. And every time I do the action, I've got this inner stream that does the retries. And another bonus point here, which I'm going to touch later, is with this sleep is not the same as thread sleep. We don't actually block a thread. When this is sleeping, your other code can use all the threads that you have. And I'm going to touch on this because it's important on the JVM. So these also make sense on its own. Repeated checks make sense on its own. Retry check makes sense on its own. And we put them back together compositionally to have this complex behavior. And finally, we do another thing that makes sense on its own, which is I have a stream of responses. I'm going to map on this stream of responses and check a field on whatever data I have that says, is everything okay or not, which is a Boolean. So the three aspects, retry and schedule and deal with the actual data, are nicely separated. And it's still purely functional, even though it's doing HTTP and timers, it's still purely functional because of referential transparency, which is what matters. And I think it's pretty cool. 3 lines, and we have done some nice business logic that we needed. So the takeaway from this is declarative control flow. What you do, normally you create a simple action in I/O, which might be wrapping some Java or impure Scala, or might be a combination of simple actions. And then you put them there together using stream. So the way I look at it when I write this kind of code, I have these little words, which are these single I/O actions, and then stream is like my stream of thought, so to speak. I weave them into this control flow using stream. And it's declarative because we use map, filter, and all these high-level combinators. We need to deal with each element. We deal with the thing as a whole. It's composable because each action makes sense on its own, and you pick a bigger action, and the bigger action also makes sense on its own. So we can keep composing. And it's obviously high level. You can get very expressive code like the retry. It's a very, very complex but very expressive. Well, not very complex, I should say, but like non-trivial logic, which is expressed in a very high-level manner. And yeah, again, we don't throw exceptions. So because I only get the question, what happens if you have errors and everything breaks? It doesn't break. We kind of deal with it, and you can deal with it as well with combinators. So this is declarative control flow with streams, and this is like the main takeaway. And now we're gonna step it up a notch. Since I didn't know like the audience level, I kind of did it in 3 steps: functional programming, what it is if you have never heard of it, and then a bit of how stream works, the basics, and then some advanced examples. So the point of the advanced examples is not to understand how they work line by line. It's just to get an idea of how the code looks like and form questions. So if there's a code snippet and it doesn't make sense, it's probably because there's a concept that I haven't explained, or you're not used to that style of code. But hopefully it's high level enough that you can get the gist anyway. And if you do understand all of it, that's great. We can talk about why it's nice, why it's not so nice, and so on. So the thing I want to talk about now, which kind of sets apart FS2 from other streaming libraries, at least historically, is concurrency. So I've told you that stream can be used for control flow, but all we see now is kind of sequential control flow. You have a stream and you do this, and that, and in a very, very sequential manner. But in actual real life, as server-side code, this is not what's going to happen. Yes, you're going to have that retry thing, and at the same time, you're going to get requests, and at the same time, you're writing to the DB, and at the same time, you need to coordinate between all these 2 things. So if you could only have one stream at a time, sequentially, you cannot implement what you need to actually write sort of real-life code. So FS2 supports concurrency. We have our own concurrency model, which is more high-level than what you get on the JVM, and we'll show a little bit about what it means, both from an expressivist point of view and from an actual low-level, okay, this is nicer than this because of this JVM thing that we don't do. So what features do we have in our concurrency model? So first of all, stream concurrency. And all I mean by this is that we can have a stream that runs multiple streams at the same time. So a stream that expresses the concept of running multiple streams. So if you look at streams, like, actually I'm going to go back to that later. So stream concurrency, running multiple streams at the same time. We have concurrent coordination and data structures. So every time you start doing things concurrently, you need a way of coordinating between them. So both in terms of synchronization, and you understand why I quoted synchronization there, and also concurrent data structures, so queues, semaphores, mvars for those of you who do Haskell, and this sort of thing, topics. We also run on thread pools. So just because you have 10 streams, it does not mean you have 10 threads. You can have a big number of streams on a small number of threads. So you provide a thread pool to us, and we decide how to run those streams in thread pool. And the pathological case is when you run on Scala.js, where we have 1 thread, and we're still running multiple streams. Lock-free and non-blocking. So this is a JVM thing. So non-blocking means, so imagine you have a thread pool with 10 threads. Most of the Java stuff that blocks, like synchronized or thread sleep, is taking that thread and putting it away. So other code cannot use the same thread until it's unblocked. So this was done when the model was, I'm going to have one thread per request. So you want a new thread, you create a new one. But threads on the JVM are quite heavyweight. You cannot have too many threads on a single machine. So it doesn't really scale. So what you do these days, you have thread pools, fixed number or a small number of threads, and you need to run stuff on those. But then if you use the normal blocking Java stuff, I have 10 threads, and I take one off because I'm doing a thread sleep, and I take another off because I'm doing a synchronized. Now I've got 8 threads. So do this enough, and your threads, you have starvation of stuff running there. So what we do the hard work for you, and all our primitives are non-blocking. So we never block a thread. So when I say stream sleep, that stream is put apart, but the thread is free for other stuff to run. And when I say a queue, a FS2 queue blocks on an empty queue, it's not thread blocking. It's the same thing. It's waiting, but the thread pool is free for other stuff to execute. So you can scale, and you don't have to worry about this aspect. And finally, it's resource safe. So that's another thing. When you deal with concurrency, you might open a DB connection or open a file, and you do all this concurrent stuff with race conditions. You want to make sure that you never leak a resource. And by that, I mean you open stuff, and then you lose it in the concurrency mess that you've done, and the thing is not closed. So you cannot close the DB connection or a socket. So we take all of that work, and we do it for you. So you tell us, OK, this is a resource that's opened like this and closed like this, and this operation returns a stream. And then no matter what you do with that stream, running concurrently, doing infinite stream, no matter what you do, we track the lifetime of that resource and make sure it's closed in every case. Exceptions, interruptions, anything. Obviously within the limit of if you unplug the machine, there's nothing you can do. But in normal scenarios, everything you can deal with manually, we try catch and concurrency, and if you've done it, it's incredibly hard. We do it for you in a transparent way. So yes, so these are the low-level features. So I want to jump back to the high-level view of why do we do this. So why we need stream concurrency? We seem if you look at stream as a sequence of operation, you can kind of look at them as kind of logical threads of execution. Rather than having a Java thread with a sequence of imperative instructions, you can look at stream as a logical thread that you can operate on with these high-level combinators that tell me how to repeat this thread, how to interrupt it, how to operate on each element. And the next step, obviously, is that you want to have more than one logical thread of execution. So support for stream concurrency makes sure that you have more than one thread of execution. And again, this is not the same as a Java thread. It's just a logical thread. It's an intuition for you. And interleaving logical threads allows complex behavior. So you might want to have one stream that reads from a queue, and the other is fetching HTTP requests, converting them and putting them into the queue. And you allow these complex things to happen via having the behavior be separated. So you have one stream that only deals with reading, and again, nice separation of concern and compositionality, and another stream that only deals with writing. And then you have a third stream that only deals with putting them back together. So even in the presence of concurrency, we still want to keep the same properties. So still declarative and composable, even with concurrency and even with mutation. And this is because of purely functional programming. You cannot get the same nicety in a non-pure way, in my opinion, obviously. So this is pure FE for the real world. People often say, well, pure FE is good when you want to run small, pure algorithms on lists, but it's not good where you have DBs and effects. Actually, it's the opposite. This is where FP shines. When you have effects and complex, actual effectful behavior, that's where FP is actually better than imperative programming. I can, if I want to, I can go and write a while loop to map rather than say map. But I will never want to write a complex concurrent thing with whiles and locks and ifs. I want to use the nice model for that thing, because that's the hard stuff. So, examples to back these bold statements up. So let's say I have a stream of file names. And the reason I've got a stream there, because it might be a pure stream. You just say, well, I want to read A, B, C. Or because of compositionality, it might be some very complex thing that reads from a database and from a cache and then returns the file names I want to read. I don't care. It's just a stream of file names to me. Same thing with a stream of output files. And I have this function from stream to stream that will do read all on the input. And again, it's not actually reading the whole thing back to streaming. It's reading chunk by chunk. It's going to send it through something. Compress deflate just zips using wrapping the Java API for like zip API. And then it's going to write it into the corresponding output. And let's say for some reason we want to do this concurrently. Perhaps for us it's better to have multiple files being partially written than having one file completed and the other one not even being started yet for some reason. So I want to do this multiple times, and I want to do this concurrently. So what I do, the first idea you can have, I'm going to say, well, I'm going to can zip ins and outs. So now I have a stream of in, out, in, out, in, out, all the tuples. And then I flat map and do copy zipped. But this will not work, because if you remember, flat map operated sequentially. So what this is going to do is going to get the first tuple, write the old file, and then go back to the second tuple, write the old file, and then go back to the third tuple and write the old file. So a flat map for us is sequential. We cannot do this, okay, I want to do this for all these streams. So what you do instead, you map first, and then you're going to get a stream of streams. And the outer stream is a stream of all the tuples, say, and the inner stream is a stream of all the write this one, write this one, write this one, write this one. And when you do join 4, it's going to run them concurrently. So it's not going to run 4 concurrently. What it's going to do is going to pull from the outer one and start it. And then when there are 4 running, it will stop and wait until 1 is finished and then start pulling the other one. So it's not actually, that map is not operating on the whole stream. It's still streaming even within the other one. Just get the first and start it, get the second and start it, get the third and start it, get the fourth and start it, or stop. There's 4 running now. Oh, the second one is finished. Okay, and get the fifth and start it, and so on. So this is a very complicated logic to implement outside of this, which we do with just a number. And if you don't care about that, you can use join unbounded. It's just going to try and start them as fast as possible. Still within 1 thread pool, though. It's not going to start creating a million threads. 10 threads, it's just going to do the scheduling for you. So this is a simple example. There's no synchronization here. And obviously, this thing is a stream itself. So now I have a stream. I don't care it's doing this parallel concurrent stuff. It's just a stream. And it just passes somewhere else. And I can keep composing that way. So let's move to a more complicated example. And I'm almost done. So yes. So I have a stream, and I want to stop this stream after a certain duration. This can be very useful. For example, I have an infinite stream that reads from Kafka. I want to read for 10 seconds and then do something else. So it's quite useful. And I don't want to specialize that thing to Kafka with whiles in that pile of code. It's a thing that can happen for any stream. I want to stop a stream after a certain duration. So how do I do that? And again, if you cannot follow all of this, it's fine. Just an idea. So I have a signal. And a signal is one of the concurrent data structures that I mentioned. And the way you can look at a signal is imagine something that's tracking the speed of a car. And you see this line going back and forth. This is what a signal does. It tracks changes of an A. So if you have signal I/O kilometers per hour, it will change when the speed changes. And in this case, I only want a stream of Boolean. I want the thing to be true and false and change. And the reason for this is because that true and false will mean stop the stream or don't stop the stream. And how do I write a stream that will, I haven't said stream so many times, it's starting to feel weird, that will do it after a certain amount of time? Simple, with the same combinators I've shown you. I'm going to sleep for the duration, and after that I'm going to use concatenation. So it's going to do that and after. And that stream is going to eval the set on the signal, which is pure, so it's an I/O. That's why you need eval. It's going to set to true. So what this thing does, it doesn't deal with stopping yet. It just deals with waiting for a certain amount of time and then setting a signal to true. That's it. Makes sense on its own. It doesn't know anything about nor stop after, and less like and about in, like not even like doesn't have any idea about in at all. Then you have out. So out, it's just gonna take in and call this combinator called interrupt when out. Sorry, S. So interrupt when takes a signal and a stream, and it says when the signal of it takes a signal of Boolean and a stream, and when the signal of Boolean changes, I'm going to stop the stream. So you can look at this as a switch, basically, on a stream. You have this signal that can be accessed concurrently, so a concurrent switch. And as soon as someone else that I don't know switches the thing off, I'm going to stop this stream and end it. So you got these two independent pieces. They all make sense. So what I want to do now, I want to create a signal. This is what stream eval signal off does. And the signal is initially false, because I don't want to, false means keep running, because the signal means stop. And then on that signal, I create the stopper by passing in the signal I want, and the runner by passing in the signal I want. And since it's the same signal, they are now sharing the switch. So the switch, you have someone that writes to the switch, the stopper, and someone that reads from the switch, the actual stream. And see, we can share state purely functionally. So another myth broken, that you cannot have shared state. You can have shared state and it's still composable and it's still nice. We're sharing this concurrent signal between the two. Now the problem now is that we have this stopper and we have this runner. And we have to find some way of running them at the same time. And I haven't shown you any way to do this. If you do ++, it's not going to work, because you're going to run this infinite one, and it's never going to get to the one that stops it. And if you switch the order, it's going to stop it, and so the one is never going to run. And flat map is the same. You're going to go into each element, then try to stop it. And the answer is a combinator called concurrently. So runner concurrently stopper is going to return runner, but also start stopper in the background. And again, this actually doesn't actually do anything. It just returns another stream that will then be translated into I/O, that will then be composed. But the semantics are runner concurrently stopper. So if we refactor this a bit, we have this thing. So yes, I take a duration and I return a function from stream to stream. It takes the input stream and creates a closed thing. It's the same code. I just renamed some variables and inline things, which I can do because this is pure. Sleep and set it true, and then create a signal and return the input one by interrupting it when the signal is set to true, and concurrently start the stopper, which will run for a certain amount of seconds, and then stop the stream. Again, traditionally this will require 2 threads, a semaphore, and while, and like ifs, and synchronize on the switch, and lots of complicated logic. This is like 3 lines, and even more importantly, this logic is completely self-contained. Doesn't matter how complicated the industry, the stream is. We have now a consent to add to it compositionally, which is interrupted after a certain duration. And this is great. And so the way we use this. Again, we have this similar, and that's why I use repeat eval print line, because it's something that doesn't make sense when you see it. And that's why it can make sense. Sure, I like printing hello for 2 seconds and then stopping. And I don't want to have, and this is the important bit, you could do it non-compositionally. In the code that does this while print, read the time and check if it's elapsed and then stop. But then you have merged the 2 concerns of printing continuously and stopping. Whereas having infinite streams allows you to split these 2 apart. And if you didn't have infinite streams, you couldn't do that. You have to add some logic to say how many times you want to run it. Whereas I can just say run it forever, and then stop this thing that runs forever, and then put it back together. And so I have this thing that prints hello for 2 seconds and then finishes. And so yeah, just go crazy. So I'm not going to talk about this, obviously, just to show you what the code looks like. So the thing on the right is a complete data pipeline. So this is going to, sorry, it's on the left. It's a data pipeline. It's going to read from a queue, think Kafka. It's going to pass the JSON, streaming. It's going to create timed windows on this. And concurrently, it's going to get the window that is ready to be aggregated, run aggregations on it, number of users per document, and then it's going to write it down to a DB, all in streaming, in like that amount of lines of code and a few other classes. The thing on the top right is a purely functional rate limiter. So you submit requests to a concurrent FS2 queue, and there's another stream that runs at the rate. So say if you want 5 requests per second, it's going to emit a tick on every 1/5 of a second and pull from the queue. And the stream you get out is the stream of request throttled. This is one of my libraries called Upperbound. And this one is a refresh ahead cache, which means it's a cache where you update timely, and every time you get the latest one. So this is all very effectful, very non-Euler problem, non-codility, very effectful server-side code of stuff that you might do in your real life and the stuff I did in my real work or open source work, done purely functionally. And I can honestly tell you, I probably will not be able to write the same code without this approach, just because I'm not good enough to all this concern in my head at the same time. But because I can split them, and because the things are so well behaved because of purity, I can achieve more than what my intelligence or talent or whatever you want to call raw skill will let me achieve. I see how even in this very complex thing, you have self-contained part. So the main pipeline, you have the parse stream that just does the parsing, you have the update window thing. They still self-contained. So even though it might look complex, it's hard, but it's not complex. It's simple because you can always understand it by splitting into parts, understanding the parts, and putting it back together. And conversely, you can always write it by writing single parts, simple single parts, and putting them back together rather than having to tackle all the problem at once. So, go wild. It's really a fun way to write code as well. So FS2 streams are very good for data that is too big to fit in memory, and they're also very good for control flow that's too hard to fit in one set. So the first one you might not encounter, but I encounter the second all the time. So yeah, thank you.
Cool. Any questions? I've always wanted to throw that out.
That's a cool microphone.
Hi.
Hello.
So, saying we would like, I guess everyone here works in systems that look as they look, and they work maybe, like for example, we work with a lot of stuff that is blocking and that is non-purely functional.
Yes.
So how, without like remaking all of our persistence layer, for example, how does this work nicely? How could we like do maybe one data flow?
Yes. So this is why they brought me in. They were like, oh no, we're doing the new stuff, it's all great, but we got this extra blocking stuff. So we do have ways of interacting with this. So ideally you should remove that. It's not, the side effectful bit, you can say, well, I don't want to be purely functional, I can deal with the complexity, but the blocking stuff, your machine doesn't want to hear about arguments, Like at some point it's blocking, the threads are going to end out. So you need to start taking it out. So the way we do it, we have custom trade pool for the blocking stuff, and then there's combinators to shift the crappy bits onto that, block on that, and then shift back. And gradually you move, this bit, I'm going to replace the blocking Kafka with FS2 Kafka, and then I'm going to replace this bit with this bit. And at the moment, JDBC is like the one that sticks. And when they finally get to write, so we're talking to Rob Norris, the Doobie author, for the longest time. When they finally write non-blocking JDBC, yes. But for the time being, to interact with side effect, you use I/O, so wrap that bit. And we have ways to interact with non-blocking side effects, which are still nice. With blocking side effect, you need to do this thread pool shenanigans for now, and hopefully we will improve the interface for doing it, and they will improve they will reduce the amount of things that do it, and hopefully you can fix that.
Hi, so if we're currently using akka streams, would you recommend looking into FS2 and any particular reason?
Yes. So this question, obviously, so this question boils down to, do you want to do purely functional programming or not? So there are other differences between the two. Akka streams is push-based, FS2 is spool-based, but they're all insignificant compared to this difference, in my opinion. And I'm not saying you should definitely do it. It depends on where you are as a team and like, do you have resources to learn? And I think Felix is doing a great job of making sure that people that do want to do that, they are able to do it. But yes, I would say so, because it's the same. That's why I have, where is it? There's why I have this slide. If you look at this code, and you look at this code, they kind of look the same. Future and IO are both the same shape. They have the same operations. But this one, you can reason about it locally. That one, you can't, because of side effects. So if you use this one, you will get some benefits. You get map, filter, you get the conciseness. And Akka stream is still concise, it's still expressive, but you will not get the extra superpower of being able to split things. And that's, for me, that's the greatest reason. Then if you have some more technical about push versus pull, we can also talk about that. But that is the main point for me.
Thanks.
So I have a question about pretty much specifically this example. So going back to where you started, you give 2 and then you add, put 2 and 2 together. Why not have the same for the future or promise or whatever you say? So you read it the first time and then it's like, the expression would be
yes.
value read from standard in, and then
that's what you do with I/O.
That would be the same thing, right?
So that's what you do with I/O. If you wanted to actually read once, you would read once and then map and do it twice. But the point.
But that's not what that slide says.
Because I have that code.
Yeah.
So if you say read. If you say read, I want to be able to express the fact that read are 2 actions. So I/O can express both read once and read twice.
Yes, and where's the read once? I think I missed that.
Yeah, I didn't write it.
Yeah,
but you just read map x plus x.
Okay.
But my point is that future cannot express the read twice.
Yes.
Right. Yeah, I didn't write that. That's why it's not there.
That's why I'm so confused.
Okay. Sorry. I will write it next time.
Yeah, another question was about, so you say that you want to run this as the last step of the program?
Yes.
Because otherwise you sort of lose the,
yes.
You go out into the wilderness, right?
Yes.
Wouldn't it be acceptable to do that if you have some sort of composed, you want to put this into some larger project and then you want to have this be your unit?
Yes, so first of all, you need to keep in mind where is Scala, right? So this is all discipline. You could have a print line in a normal one and everything is good. Yes, it is acceptable, but you're losing the fact that component, when you do unsafe thing, that thing is now not referentially transparent. So inside the thing, you get the benefit. Outside of it, you don't get it. And so if you do it as the last thing, the code that doesn't get it is non-existent because it's the last thing. But yes, it's acceptable. If you want to migrate, you say, well, I know that this cannot happen because I need to embed it, but inside this is my nice world, and outside it isn't. You can do that. Yes.
Yeah, because the problem is that normally you start in the world of the savages, and then you sort of introduce the.
Yes. So the reason. So normally we say at the end of the world, and people get confused. That's why I said the last thing. But the end of the world changes depending on your code. In an ideal world, or my world, the end of the world is the end of the program. But it might be the edge with the legacy. That's the end of your world, and so you do it there. Does that answer your question?
Yeah, that's cool. Absolutely it.
Any other questions? Right, just one last thing. If you want to talk to me after, or in the following days and months, I am on Gitter. I'm not on Twitter, but I'm on Gitter and GitHub as SystemFomega, spelled SystemFW. I'm very friendly. I'm there. Don't be scared to either DM me directly or come into the channel FS2 Cats. You're going to find me anywhere, pretty much. So if you have a question and you're not quite sure how to formulate it now, please reach out, and I'll be glad to talk to you. And thank you very much for having me. It was great.
Thank you very much, everyone.